All right, let's dive in. Today, we're going to unpack a really powerful tool in statistics, one that helps us predict events that seem totally random. We're taking the Poisson Probability Distribution from something that might seem confusing and turning it into a tool you can actually understand and use.
I mean, really think about it. How do city planners figure out traffic flow? Or how does a company know just how many people they need working in customer service on a random Tuesday afternoon? It all seems random, right? But it's not quite as unpredictable as you might think.
These kinds of things are actually perfect examples. The number of emails you get in an hour, the number of typos you spot on a single page, cars passing a certain point on the highway, or calls hitting a support center. They all feel like they happen randomly, but believe it or not, there's a pattern we can actually model.
And that is exactly where the Poisson distribution shines. It's this fantastic statistical tool designed specifically to model the number of times an event happens within a fixed interval, whether that's an interval of time or space. The whole thing is built on what's called a Poisson process, and the core idea is pretty simple. We're just counting how many times something happens inside a set boundary. That boundary could be an hour, a square meter, or even a kilometer of road. Now hold on. You can't just use this for any old random event. There are some specific conditions that have to be met. You can think of them as the rules of the game that let the Poisson distribution work its magic.
Okay, so rule number 1. The events have to be independent. An email arriving at 10:05 a.m. doesn't make another one more or less likely to arrive at 10:06. Rule 2. The average rate has to be constant. So you'd expect about the same number of cars to pass a quiet corner at 3 a.m. on any given Tuesday. And finally, Rule 3. The chance of 2 events happening at the exact same microsecond is basically 0. All right, here it comes, the part that can look a little scary. The formula. But don't you worry, we're not just going to stare at it. We are going to crack this code together, piece by piece, so it actually makes sense.
So, here she is. At first glance, yeah, it might look like a jumble of Greek letters and symbols, but every single part has a very specific job. We've got lambda, our average rate, t, our time interval, x, the number of events we're testing for, and that little x with an exclamation point, that's x factorial. Let's break down what each bit is actually doing.
Let's call this first chunk lambda t to the power of x, the weight. Now lambda t is the number of events you expect to happen. By raising it to the power of x, the number you're actually checking, this part of the formula gets bigger when your target number is closer to what you expect. It gives more weight to the more likely outcomes.
Then you have this second part, e to the negative lambda t. Let's call this the decay. This is like the brakes on the system. It makes sure that the probabilities for really high, super unlikely numbers get teeny tiny, which is what they should be. It keeps the whole thing balanced.
Okay, so now that we've wrestled the main formula, let's look at something beautiful, a wonderfully simple shortcut that the Poisson distribution gives us for finding the mean and standard deviation.
Check this out. The mean, the average number of times you expect something to happen, is just lambda times t. Simple. And the standard deviation, which tells you how spread out the data is just the square root of that exact same number. This leads to a really special property.
And this is just so cool. It's a totally unique feature of the Poisson distribution. The variance is literally equal to the mean. That means the standard deviation is just the square root of the mean. It's an incredibly clean and useful feature you don't see in many other places.
Okay, theory is great, but the best way to really get this is to see it in action, right? Let's walk through a practical example together.
Okay, so let's imagine a call center that gets, on average, 3 calls per hour. That's our lambda. Our interval t is 1 hour. And what we want to know is, what's the probability of getting exactly 2 calls in that hour? So our target, x, is 2.
First up, let's calculate the mean. That's a piece of cake. It's just our average rate, lambda, times our interval, t. So, 3 times 1 gives us an expected average of 3 calls per hour.
And because of that really slick shortcut we just talked about, the standard deviation is just the square root of that mean. The square root of 3 is about 1.73. See? Easy.
All right, here's the main event. When we plug all our numbers into that big formula, we find out that the probability of getting exactly 2 calls in that hour is 0.224. In other words, there's about a 22.4% chance of that specific thing happening.
But we can do more than that. What if we want to know the probability of getting at most 2 calls, so 0, 1, or 2 calls? Well, we just calculate the probability for each of those and add them up. And what we get is 0.4232. So there's a 42.3% chance of the phone ringing 2 times or less. You can see how useful that is for staffing and planning.
And there we have it. We went from a mysterious formula to a practical tool. You now have a way of thinking about and even predicting the frequency of things that seem random. So I'll leave you with this question. As you look at the world around you, from your email to the traffic on the street, what could you start to predict?